All right, today we're diving into the rudder and the steering gear. They're two of the most critical pieces of equipment for keeping a massive ship under control. Just look at this thing. It's an incredible shot of a ship in dry dock. You can really get a sense of the massive scale here. And right there, tucked behind that giant bronze propeller, is the rudder. And honestly, it looks almost tiny in comparison, which brings up a really good question. So how in the world does that little fin manage to steer this entire floating city? Well, the answer is just a masterclass in engineering and physics, and it's probably not what you think. It all starts with what we can call the rudder's dilemma. Picking the right rudder, its size, its shape, where you put it, these are some of the most important calls a naval architect has to make. It affects everything from how much fuel you burn to whether you get home safely. Okay, so the secret to making it all work is something called the propeller's outflow. That's just the super high-speed jet of water getting blasted back by the propeller. You absolutely have to place the rudder right in that stream. It's kind of like sticking your hand out of a car window on the highway. The faster the air, the more force you feel. The rudder's harnessing that focused energy to get all the leverage it can. Now, of course, it's not a one-size-fits-all deal. Engineers have come up with a whole family of rudder designs, and each one is a specific solution to a different problem, whether it's about efficiency, control, or just pure safety. Take a look here. On the left, you've got a balanced rudder, and on the right, an unbalanced one. Now, look really close at that pivot point. It's called the rudder stalk. See how it moves? That one little change, well, it has huge consequences. So with the balanced rudder, about 40% of the rudder is actually in front of that pivot point. It's a really clever design because it uses the water pressure on that front part to help turn the rest of the rudder. This cuts down the amount of torque or twisting force that you need. And less torque means you're using less energy, and that means better fuel efficiency. The unbalanced design is simpler for sure, but man, it takes a lot more muscle to turn. So what's the modern solution? The semi-balanced rudder. It's kind of the best of both worlds. You get the efficiency of the balanced design, but with more structural support. And here's the brilliant part. It has this key safety feature where if the steering gear completely fails, it's designed to naturally swing back to the center. That gives the crew precious time to figure out what to do next. But engineers are always pushing the limits, right? So you get some really cool out-of-the-box designs. The flap rudder actually has flaps on it, just like an airplane wing, to get way more turning force. Perfect for ships that have to be super nimble. Then there's the Pluga rudder, which has its own little propeller built right into it for amazing control at really slow speeds, like when you're docking. And the Void system? The whole thing is one unit, propulsion and steering all rolled into one. Wild stuff. Okay, so now we get to the part that kind of blows your mind a little bit. How a ship really turns. And I'm telling you, it's not what you think. I mean, the common sense idea is that the rudder just acts like a big paddle, right? It just pushes the back of the ship to one side. But that's not what happens, not even close. The rudder doesn't actually provide the force to turn the ship. It's more like a catalyst. It just kicks off a chain reaction. In reality, it's this amazing 5-step dance between the ship and the water. It goes rudder force, then rudder moment, then drift angle, inertia forces, and finally, the hydrodynamic moment. That last one is what really does the steering. So let's just walk through it. Step 1. The helmsman turns the wheel to starboard. That's to the right. The rudder moves right. But here's the first weird thing. This creates a lift force that pushes the stern to port or to the left. Yeah, you heard me right. The ship's stern initially sways a little bit in the opposite direction of the turn. Step 2. That little push creates a tiny twisting effect around the ship's center of gravity. We call it a rudder moment. But, and this is absolutely critical, this moment is incredibly weak. I mean, there is no way it is strong enough to turn a 100,000-ton ship on its own. So what's the point? Well, step 3. Its only job is to create a tiny little drift angle. All it does is slightly cock the ship's nose so it's pointing just a little bit away from the direction it's actually moving. This tiny angle, this is the linchpin for the entire maneuver. It's like setting up the first domino. And now, for step 4, this is where the magic happens. Because of that drift angle, the entire side of the ship's hull is now pushing against the water. And the water, because of inertia, does not like to be moved, so it pushes back. And it pushes back with an unbelievable amount of force. We're talking a force that can be equal to the entire weight of the ship.
And finally, step 5. Because of the shape of the hull, that pushback from the water is way, way stronger at the front of the ship than it is at the back. This imbalance creates a massive turning force, the hydrodynamic moment. And that is what powerfully swings the bow into the turn. So let's say it again. The rudder doesn't turn the ship. It just cleverly gets the water to do all the heavy lifting. It's absolutely genius.
So we have this incredible fin that uses physics to do its job. But what's actually moving it with that kind of precision and power? Well, that brings us to the muscle behind the whole operation, the steering gear. And this machinery has to be seriously powerful and fast. I mean, there are international safety laws, the Solace regulations, that say a ship's steering has to be able to move the rudder from 35 degrees on one side all the way to 35 on the other in just 28 seconds. And that's even when the ship is at full speed. That's for those emergency moments when you need to turn, and you need to turn right now. So how do they do it? With hydraulics. And there are basically two main flavors. You've got the ram type, which is just pure brute force, giant hydraulic cylinders that create incredible torque. And then you have the rotary vane type, which is a bit more compact and is perfect for saving space down in a crowded engine room.
You know, the true test of any system is what happens when things go sideways. And a steering gear failure isn't just an inconvenience. It can lead to an absolute disaster.
Think about this real-world story. A vessel's steering just died in a narrow waterway. The crew scrambled, they switched to the backup system, but by the time control was back, it was too late. The ship ran aground, causing huge damage. It's just a stark reminder of the massive stakes involved. And you can see why marine engineers are completely obsessed with this system. They're in a constant state of vigilance, looking for hydraulic leaks, any mismatch between what the helm is ordering and what the rudder is actually doing, strange noises, high oil temperatures, really anything at all that could compromise this absolutely critical system. So let's put it all together. The steering gear provides the muscle, the rudder is the clever catalyst, and the water gives all the real force. But that kind of brings up one last question, doesn't it? What generates that powerful flow of water that the whole system depends on in the first place? Well, that's a story for another explainer.